Hi, Violet. I'm going to teach you something very important, and I need you to listen up, okay? I'm going to tell you about ion concentrations, okay? Ion concentrations. So, I need you to know that there's potassium, there's chloride, sodium, and calcium. So remember that potassium is higher inside. So remember that you are my kin. Okay? Remember that. You are my kin. Because potassium is in. The other three are out. Chloride, sodium, and calcium. Hey, are you catching this? Are you catching this? Okay, so it's important to remember what the chemical gradient is and the electrical gradient. So I'll do chemical in purple. So the chemical gradient wants to go where there's less of this. And there's less of potassium on the outside. So it's going to want to go out. Chloride, whatever, it's going to go inside because there's less of it inside. There's less of this on the inside, and there's less of calcium on the inside. Okay, now, hey, bye. Remember that the electrical gradient wants to go to the opposite. So if it's positive, it will want to go where it's negative. And if it's negative, it'll want to go where it's positive. Hey, don't interrupt. Okay, sorry, that was mean. You can just keep talking. Okay. So it's going to want to go to the opposite. So potassium wants to go where it's negative, and it's more negative inside the cell. Chloride will want to go where it's positive, so it'll want to go outside. Sodium will want to go inside because it's positive, so it'll want to go where it's negative. And calcium will want to go inside. Yeah? Got it? Hey, look. Got it? Got it? Don't forget it, Kay. It will be important. Okay, Violet asked a really good question. If potassium is positive inside the cell, then why is it negative inside? That is a really good question. And I'm going to tell you right now, but it's not the point of the video, so I'm going to say it really fast, okay? There are three things that are making the inside of the cell negative. And these are also the three things that are establishing resting membrane potential, which is negative 70 mV, right? We talked about that earlier. Okay, so the three main things, let's pretend this is the cell, and I only have one hand, so this is really, really pretty. The three things are the sodium-potassium pump, which remember, does 3 sodiums out and 2 potassiums in. So if it's pumping all of these, wait, why is that negative? If it's pumping 3 positives out, it's obviously going to be more negative in, because if you're taking all the positive out of somebody, then what's left inside, right? They're not putting enough positive back in. Okay, another thing keeping it negative is the negative charged proteins. And obviously, if there's negative charged proteins inside, then it's going to be pretty negative. Okay, I'm just going to say negative charged proteins. And the third thing is the potassium leak channels, right? So if potassium's constantly going out, then it's going to, sorry, this is not very pretty. Then it's obviously pumping all the positive out, kind of similar to the pump. And what's left? What's left? I don't know. Remember that the cell membrane is permeable to only potassium. Okay? Okay.
Okay, the first thing we're going to talk about is action potential. And there are 2 channels that are part of the cell membrane that allow for action potential to happen. And those 2 things are the sodium voltage gated channel and the potassium voltage gated channel. And those look like this. This one is the sodium voltage gated channel, and I don't know if you can see it very good, but these doors flip open and close really fast. And this is the potassium gated channel, and it opens and closes very slow. Okay, the first part of action potential is a stimulus. So if we are touched on our skin, that increases our cell membrane's permeability to calcium, which is a positive ion, like we talked about earlier, right here. And if we have a positive ion rush into the cell, that will, let me share my whiteboard. That will give us a positive response right here. When it hits threshold, our sodium gated, or sodium voltage gated channel is going to flip open. It's good to know that when it's at RMP, the bottom is already open. I drew it wrong. So when it's like resting down here at -70 mV, this inactivation gate is already open. When it hits threshold, this top part flips open super fast, and sodium starts rushing in side of the cell membrane, making the inside more positive. Okay, and the potassium channel slowly starts opening, and potassium is slowly exiting. Okay, when it reaches the top, which is whatever, someone needs to help me with that. When you hit the top, or when you have all the sodium coming in and not very much coming out, I think it is going to kind of start leveling out, and it will start going down because this is going to flip closed. The sodium voltage gated channel is going to flip closed. Let's see. And when that flips closed, this is still open. So that's going to start making it more negative, because if you have all these positives leaving, the inside's going to start becoming more negative. And that's how come our thing starts coming down. And that is called repolarization. And you just kind of remember that because it's kind of going down. And this is depolarization, right? When it goes up. Okay, so it's coming down, repolarizing, and this is fully open. And the more that leaves, the more the potassium leaves the cell, the more negative it gets. Okay, this door on the potassium voltage gated channel starts closing. Sorry, this is kind of ugly. It slowly starts closing. And as it slowly starts closing, potassium isn't allowed to leave as much. And that causes it to come even lower than -70 mV. And that is called hyperpolarization. And what brings it back up to -70 mV is when the door is fully closed. When this is fully closed and nothing else can get out, it comes back to -70 mV. Two things to remember: that the membrane is only permeable to potassium ions, and the sodium pump is working to maintain the gradient. And anyone can correct me if I said anything wrong. And that's all. Goodbye.